This is the second lecture of the vision module in the F1TENTH course. Today, we'll talk about deep learning methods to show you how deep learning has revolutionized the field of computer vision. So last class, we have talked about classical methods. In this lecture, we'll first go through some deep learning basics. I know many of you have learned deep learning to different levels. So for those who are not familiar with this topic, I'll talk about some concepts so that we can get started for the two case studies of object detection. First is YOLO. The second is object detection with point cloud input, PointPillars. Then I will talk about two topics in the recent trend of computer vision. And last but not least, I'll talk about network deployment. First, deep learning basics. We all know that deep learning can do object detection, right? We can draw bounding boxes around the object in the images. Here, I just want to show you what are other fantastic tasks we can have the neural network do for us, particularly in the field of autonomous driving. So here you can see we can get 3D object detection just from monocular camera. This is just using this monocular camera image is drawing the 3D bounding box to show you where the object is and how deep it is. And on the right, you can see the network also outputs a bird's eye view to show you from the top-down view how far the object is. And over here, you can see this is the optical flow. We can calculate optical flow in the classical computer vision. It's just that we find some feature, and between the frames, we can match the feature to track how that pixel is shifted between the frames, right? In the deep learning field, we can also train a neural network to, we input 2 frames and the neural network output a optical flow. This is sometimes even more accurate than the classical way of calculating it, just because the classical way involves feature matching, which is noisy sometimes. Here you can see this is a semantic segmentation. This neural network takes in this input and output a semantic classification of different pixels to show that which part is the paved road, which part is the not so good condition road, and which are the areas we should avoid, and which are the lane markers. So from this kind of deep learning neural network, we can find where are the drivable surfaces and where are the obstacles that we should avoid. Here is an example of LiDAR point cloud detection. So for LiDAR point cloud, we have a 3D point cloud with distance information, but also this distance information is not distributed evenly. You can see it's dense over here, it getting more sparse when we go further away from the LiDAR. How can we build a neural network that takes this kind of data to do 3D bounding box detection? Here are 3 examples of like more fancy application you can find with deep learning. We can get more depth from monocular camera. Even human sometimes have difficulty just to infer which object is further away if we close one of our eyes. But with the correct data and ground truth, we can train the neural network so that it would be able to infer the distance of this scene just by looking at one frame from the monocular camera. In the center here, we have a dehaze network. So this is not just a like a sharpening filter applied onto the input image. It's actually inferring with the knowledge, like for example, how this car should look like if there is no haze in the environment. So in this paper, this person claims that with his dehaze neural network, the object detection algorithm actually performs better than just doing this raw input. Over here, we can see this is a neural network that can convert a night scene into a day scene. So this one is the input, this one is the output. We can see far more detail in the daytime scene than compared to the night scene. Of course, this is based on a GAM structure, so it's more like it's inferring, uh, it's imagining what are the scenes inside this darkened field. So it's not guaranteed that it's showing the authentic material. But of course, those topics are still in Switcher's topics. I just want to show you that there are a lot of this potential fantastic things we can get from deep learning. Okay, so last time we talked about classical machine vision. And in classical machine vision, there is the one important topic of feature extraction. If you want to detect an object, we have to find its features. So we can use different kind of kernels to detect different features. But last time we only talked about simple features, for example, this corner detection or edge detection. So instead of just corners and edges, can we work with higher level features? For example, can we detect this person on his own? And do we have to design the corners with our hands? I mean, of course, the answer is that deep learning can help us do that. We can see from here, if we are using a rule-based system, we have to design everything. We have to hand design the whole program. And if we use the classic machine learning algorithms, we still have to hand design the features, but we can use a machine learning algorithm that use the combination of these features to learn a certain detection method. So in terms of deep learning, we're not making the features by hand. We're also not making the combinations of these features by hand. We're not making the mapping between the feature and the end output by hand. And so everything is learned. What we have to do is we have to design an architecture that extracts the features from the image, then it maps them onto the labels that we want it to learn. We also have to design a loss function that act like a guide for this neural network to learn the material that we want it to learn. So the architecture, both the architecture and the loss function are important in the deep learning. So feature extraction in deep learning, we primarily use convolutional neural network to do this. If we look at the diagram over here, the lower level convolutions will output low level features. It's usually edges or maybe corners in some channels. Then there is mid-level features. That's a combination of the lower level features. Of course, there are higher level features. Then at the end of this line, we usually have a trainable classifier that maps these features to the label that we want. The label could be a object class, could be a bounding box, or other things. So the convolutional neural network is, we use a hierarchy of convolutional kernels to detect a feature at different levels. Then we also use a nonlinear activation function at each layer to catch some nonlinear information. We use machine learning methods to train the neural network for useful kernels. At the end of the neural network, we use a classifier to map these features to outputs. So this is a very simple, this is the structure of YOLO, that after the input, you have a series of convolutions that extract the feature from low level to high level. Then you have a classifier that will regress the class, the bounding box position, and others that you want this neural network to learn. So the common detection structure is like this. You first need to pre-process the data. You need to resize the image, normalize the pixels. Then there is a feature extraction part. It's usually also called backbone. We usually use CNN, convolutional neural network, to extract features. In this part, there can be skip connections, which means that you can directly pass lower level features into higher level, or pass the lower level features directly to the classifier so that they can take different levels of features when doing the regression. There's also a tendency to use a bottleneck design. The bottleneck means the channels of the convolutional neural network shrinks in somewhere in the center of the neural network, and it expands later. This is trying to force the neural network to learn some kind of a latent space or some kind of a low dimensional representation of the input. Then after that, we usually have detection heads. Depending on the different functions that you want this neural network to do, we can have a object detection heads or key point detection heads, 3D bounding box heads, etc. And after that, there is result decode and post-processing part. We need to filter out low confidence results. And sometimes we need to do a non-maximal suppression so that we don't have repeated detection of the same object. So the structure of the neural network determines its function. And for object detection and many other tasks, this backbone plus detection heads, it's a common structure. So here I just want to go through what is the neural network doing when it's training. First, we need to prepare labeled data. This is not just labeling the data with bounding boxes. This is preparing the image and the ground truth in the format that we want this neural network to learn. So the ground truth can be object class, object existence for detection, the size, or anything you want the network to learn. Then we need initialization. We start with some random numbers, or we can pick a pre-trained neural network, or we can pick a part of the pre-trained network and plug in your own design at some point. This is a very useful way when we do the transfer learning to save time and resource. Then there is forward propagation. That is, we take the neural network with the weights inside it. We plug in the input. We calculate with the current kernel through the neural network until the last layer, and we compare the current result to the ground truth, and we calculate the loss function. And with the loss function, we do the back propagation. Is that we calculate the derivative value of each variable inside the neural network with respect to the ground truth, or with respect to the loss function. Then we adjust the network based on that. So during the back propagation, the batch normalization is usually done. The batch normalization is that these adjustment that we need to do on the neural network needs to be normalized within a batch of training data. For example, if we have 100 images, we can have a batch size of 10. So when we do the back propagation, we need to normalize the changes we want to do within these batches. This is an important step for your network to really learn some general knowledge of the things that you wanted to learn. So if we put it into a diagram, it will look like this. We first do data preparation, initialization, the network do forward propagation, backward propagation, then we update the weights. And this step will just repeat until how many epoch we want it to do. And the whole process will repeat because we want to change the neural network. For example, we want to do experiment on it. We want to add or remove a layer. We want to change the number of channels in a certain layer. Or we want to add drop-off pooling layer, or we want to add skip connections. So each time we do changes with the neural network, we just do the training again to see whether we are improving or not. Also, we need to do hyperparameter tuning. Like we need to try different learning rate. We try different convolutional kernel sizes or other things just to make sure that we are we're scanning the whole space to find the optimal training result. So this is a training pipeline of the single neural network. However, training is only just one part of the whole life whole life of the neural network. In the beginning, we need to do data collection, labeling, and augmentation. Then we need to select based on what functions that you want this neural network to do. We just select from existing designs, or we can do our own design. And after the training, we need to deploy the neural network to some platform. Then after we deployment, we want to do lifelong updates, is that we can actually get additional data from the deployment and pass back to the data collection to the training to further improve the performance of the neural network. So training is only one part of the network's life. Data collection and labeling are the time-consuming part. The network design is the technical part because you have to just try a lot of designs. The network deployment is usually the consequential part, because even if you train a very good neural network, how you perform in the end will largely depend on the device that you are doing the deployment on. If you cannot deploy it onto a suitable device in a suitable way, then the end result may not be as good as the training shows, right? Because depending on the performance of the chip. And the lifelong updates is usually a legal part, because we want to get data from the deployment platform, which will probably be the user, the end user. And if we want to get data from them, there could be some legal issues with that. After the basics, I want to do two case studies. The first one is image detection with object detection with image. What to introduce you to YOLO. So YOLO is a single-stage object detection architecture published in 2015. YOLO at that time was considered fast, fairly accurate, and structurally very simple. It is to this day considered structurally very simple. That's why it's a very good introductory neural network. So YOLO has some issues, like there are too many phase positives and requires very heavy post-processing. It is old, but it's a very good way to learn the neural network in computer vision. So this is the structure of the YOLO. So this part is the feature extraction part. You can see there are several layers of the convolution neural network. You don't need to worry about those dimensions because those are just the author's choice. They're not necessarily the best choice. So what we want to pay attention to is the last layer. The last layer is 7 by 7 by 30. So why is the 7 by 7 by 30? So 7 by 7 is because this input image, any input image, is being divided into the 7 by 7 windows. And each window has 30 channels. That's why the last layer dimension is 7 by 7 by 30. So 7 by 7 is just the output dimension of the convolution. It's just set up so that from the input data, after all those convolutions, you end up with 7 by 7. Of course, you can do any grid dimension you want. You can do 10 by 10. This is just how, depending on how you set up your convolutional part. So each window proposes 2 objects, and each object has 5 parameters. So each object, that means it's an H detection, right? So for a bounding box, you need to have a XY position and width and height. You also need to have a confidence value. It is 1 when there is an object, when it is 0 when there is an object. And so there are 5 parameters for each bounding box. And then for the original paper, it has 20 values for object classes. So there's another 20 values for each window that propose the class of this object. So in total, there are 2 times 5 plus 20 equal to 30 channels. So the YOLO ground truth is set up so that each window, like, it's independent of the other ones. Of course, the information is it's related to other windows by doing the convolutions. But the ground truth, for each window, there are 2 bounding boxes, and there are 20 values for classes. That's why it's in total of 30 values. So here is the loss function. You can see this is the XY coordinate loss. This is the width and height coordinate loss. This is the confidence loss. This is confidence loss with if there isn't an object. So this value is a very small value. That means this is just a saying that if there's no value, that don't count too much into the total loss. And then here is the value for each class. Are we getting the correct class for this detection? So how YOLO detects? As we just said, in total, there are 7 by 7 by 30 tensor outputs, right? So this 7 by 7 comes from the convolution. It's because this author divides the input image into the 7 by 7 grid. 2 of the 5 parameters per grid, and there are 20 classes. So the detection logic is very simple. So for each grid, if this confidence value, if there are 2, it's the higher confidence value, right? If there are a confidence value greater than the threshold, then we just pick that detection with the highest class. So there are 20 class proposals. We just pick whatever the highest value in those 20 class proposals. So as you can see in this diagram here, so there are a lot of bounding boxes. That's because each grid proposed two bounding boxes, and we have to confirm that this bounding box confidence value is greater than the threshold. And for each grid, there is a highest class value. So if there's a bounding box that's past the threshold, then we just pick whatever the class this grid is. So what do you think is the limitation? One very straightforward limitation is that each grid can only have one class. That means for each grid, even if there is 2 objects over here which belongs to 2 different classes, we can only detect one class in this grid, right? Another limitation is that we're doing 2 of the bounding boxes, but what if the input, like the output dimension is now 7 by 7? What if there are a lot of objects, right? We're limited by the amount of grid or the amount of bounding box we set inside the dimension. So in terms of this dimension, 7 times 7 times 2 is the highest amount of object you can detect in this frame, right? So these are the 2 primary limitations in YOLO detection. Another limitation is that we just said there is a threshold on confidence, right? But sometimes it's not enough. Maybe this bounding box comes from this grid, and this bounding box comes from just a neighbor grid. They're actually detecting the same thing, but there are two bounding boxes. So we have to do this non-maximal suppression to select which one is the best bounding box. So the non-maximal suppression just says, okay, I calculate this IOU intersection over union value. If this value, if 2 of this bounding box overlap basically is, then we just consider that one bounding box with the highest confidence score, and we just disregard any other bounding box that's overlapping with this one. That's the non-maximal suppression. So you would imagine you have to go through a lot of bounding boxes in this detection result to filter out which one is the best results. So that's another thing about YOLO. But in terms of its structure, as you can see, it's very straightforward. So we will do this training with a PyTorch code in the lab, and you can see in a very quick time, it will converge to some detection. So here is a diagram that shows what's the development of object detection in the past 7 years. YOLO is probably around here. As you can see, we're almost double the performance 5 or 6 years ago. So I can see YOLO over here. YOLO v4 is still the YOLO YOLO-ish architecture, but it has a lot of improvements on different parts. And the most recent ones, they all use the convolution. They don't use convolution as feature extraction. They will use transformers as feature extraction, which we will cover briefly later in this lecture. Okay, next case study, object detection with point cloud. The network we want to introduce is PointPillars. It's doing object detection on point cloud data. So point cloud data is a list of unsorted XYZ coordinates. They are points that the LiDAR detects inside the real environment. So as you can see here, this is point pillar detection results. They don't use RGB image when they're doing when they do the training. You are able to incorporate them into the training pipeline, but that's a different architecture. So for this simple architecture, they are just inputting the point cloud data, and they could do 3D bounding box detection just on the point cloud data. So some challenges with this. LiDAR point cloud is very sparse, and it's uneven. Sometimes it's sparse, sometimes it's quite dense when they are close. And if we're just gonna do like binning into like a voxelization, binning into small bins, and just do 3D convolution on that, that could be, the complexity can be very heavy. There are neural networks that prior to PointPillars that does this, but it was very slow and very expensive in computation. And the results are not very good either. So this is the PointPillar structure. Well, the smart trick of this PointPillar is that it's still using the 2D convolution. The first step they do is they combine this sparse point cloud into pillars, and they align the pillars into pseudo image. The difference between doing the voxelization and this way of aligning the pillars is that the 3D convolution, the 3D voxelization actually preserves the 3D distribution of the voxels, right? You can still see this is an airplane, but this one is they bin it into the pillars, and they just align them into an image. So some of the 3D dimensional thing could be pressed and misaligned, but it doesn't really matter. So onto this pseudo image, they do a traditional, like a 2D convolutional neural network, a 2D backbone, and after that they do a 2D detection head to regress this 3D bounding box. So the benefit of this is that you can have a lot of different choice of backbone, different styles of backbone and detection head you can plug into this. They are efficient, unlike 3D convolutions, which are very expensive to do. And they can do quite good detection with this kind of structure. So I want to talk about 3 recent trends in computer vision. These are a more interesting topic than the 2 case studies that we just see. First is a GAN-based method. So GAN-based method is it's used when we want to train some generative neural networks. It's called generative adversarial nets. So it's training a generator and a discriminator at the same time. That's why it's called adversarial. So Here it's called latent space, like it's some low-dimensional representation of the image, of the information that's inside the image. So we have some input to the generator. It outputs an image, and we feed this into the discriminator along with a real image. And the discriminator should distinguish whether this one is real or not. So the purpose of the generator is to generate an image that tries to fool the discriminator, and the purpose of the discriminator is try to compete with the generator just by showing that, okay, we'll take the fake image, like even if it's perfect, I'm still able to tell you're fake. And you do a loss function over here and a loss function over here as well. And you can train the two networks together. So these are used when people like generate these fake faces, which we all know, right? So what can we use for the game-based method for autonomous driving? So here is this night to day neural network. It's pretty complicated, right? This is like the state of art computer vision research now. So let's look at the testing pipeline, the inference pipeline first. I have some legends over here. E is for encoder. G is for generator, right? Yeah, and we will see this in this part. So encoder is we take an image and we output some latent space, output some lower dimensional representation. Then the generator takes in this latent space and outputs another in between image. So they have a translation stage. Basically, it's from a night scene into like a neutral scene, and this refinement stage takes a neutral scene and outputs a refined day scene image. So this is the testing pipeline. Let's look at part of the training pipeline. So this is the input. The input is a night scene image, but we don't have a day scene image, right? So we actually don't know what this thing should look like in reality, in daytime. So how can we train this? So the logic they used is that we have to find some latent space that's representing what is inside this scene, like so the logic they use is that we can find some latent space that represents what is happening in this scene, and it doesn't really matter whether it's daytime or not. So it's using a encoder to find this latent space from the night scene, and it's also training a generator that takes in this latent space and generate a night scene image. And if this one and this one are correct, then we should get a result that's the same as the input, right? Because we are correctly encoding the information into the latent space. Then they have another pipeline that takes this into another generator and generate a daytime scene. Another encoder to encode into this daytime in latent space, and another generator turn it back to the night scene. So if all the pipelines are correct, that means this latent space should be the same as this latent space, because the latent space should be representing the essential part of the image, regardless of whether it's a night scene or day scene. And it has this discriminator to compare whether these images are the same or not, are false or true. He has another symmetrical pipeline that's trying to train all those neural networks to generate this another latent space. So as you can see, in this type of neural network, it's very complicated because we don't actually have the real data that we want the neural network to learn. But we have the knowledge to design some abstract architecture so that we can guide this neural network to learn some latent space, to learn some abstract representation. Another topic I want to talk about is transformers. So these are widely used in the computer, in object detection in the last 2 years, and it outperforms CNN. So transformers are previously widely used in the natural language processing research. So it's basically in natural language processing, if you have a sentence and you have words in the sentence, right? And for each word in the sentence, you calculate the tension with another word to see which word is the most important and what's the relation of this word with each other words in a sentence. So when it applies to the computer vision field, for example, in this paper, it's the same thing it's the same thing as in YOLO, that you split the image into different patches. And each patch, you consider it as a word in a sentence. So if the image is a sentence, then each patch is a word. And in each word, when it pass, in each patch, when they are patched to the transformer encoder, the transformer is calculating this multi-head attention. So the attention calculation process will look like this. It's like for each patch, you would calculate what is the attention with all other patches. And when we get to the end, there is a loss function to guide the training of this so that it's able to calculate the correct attention map. So as you can see here, it's a very expensive way of calculating the relation between its patches here. But if we want to do, like, for example, object detection or semantic segmentation, that's on the pixel level. So it's a quite expensive way to compute this. But one advantage of this one compared to the CNN is that when we're doing the convolution, in the shallower layers, in the low level features, you're only detecting some features around the neighborhood of this pixel. And it's only until the deep layers you're able to relate, for example, this corner of the image with this corner. So, but at the shallower layers, they couldn't relate because the convolution just cannot do. The convolutions doesn't have enough receptive field to do that. But when we calculate this attention map, each patch actually get to talk to the other patch. I mean, that's just the logic that people are giving these transformers for now. The third topic I want to cover is called multi-camera fusion. So we can just use the slides from the Tesla AI Day. So what they are trying to do is for the cameras on the Tesla car, they want to fuse them together to do the object detection. As we talked about last time, right? It's not really difficult. I mean, apparently, you just have to do the camera calibration for each image onto the world frame, right? I mean, not the world frame, onto the car frame, right? But it's actually when we do the camera calibration, we always have an error. We always have a noise. If it's just one camera, that's okay. But if you are fusing different cameras, the noise just multiplies. So what they did is they all calibrate the cameras into a virtual camera. They add a camera calibration layer into their neural network. So these are different cameras, and they all calibrate into a virtual camera. And they go pass through the neural network, and they go to the feature extraction. You can see over here, they use transformers for the feature extraction. And they encode the positional thing inside the feature extraction as well. And they have detection heads over here. So what they can do with this architecture is that, for example, you can see over here, for doing link detection. So this is the result they can achieve when they do the detection with single camera and fuse the detection together after detections, right? So, but this one is they use this one single neural network to do the detection, fusing all the multi-camera inputs. You can see the detection result is much better. So another thing they can do is they can do ops detection. For example, the orange one is the single camera detection results. The blue one is with multi-camera detection results. With multi-camera, you just have more information. And the key is how do you fuse them together, and so that you get a noise reduction compared to detecting with the single camera. So I think this is quite fascinating results. Okay, the last topic I want to talk about is network deployment. Network deployment is optimizing the size and speed of the network for the particular platform that you want to deploy the network on. There are three common techniques. You can do network pruning, you can do network quantization, or you can do some platform optimizations depending on what type of platform you're trying to use. Here's an example of quantization. This is comparing the speed. If we run the network in FP32, that's single precision, or if we run the neural network in integer. I mean, of course, the running in integers is much faster. Is the only thing is how can we achieve the same performance when we run it in integer, right? Here is an example of pruning. Pruning is like cutting out the useless part of the neural network. It dramatically reduced the size of the neural network, but maybe it sometimes can even improve the accuracy. At least it didn't reduce the accuracy. However, we're not sure that after this kind of cutting, is the neural network still the same? Is the robustness reduced? So we have to do a lot of testing after we do this. And safety can be also become a concern. For example, if this neural network is responsible for like detecting doing facial recognition, if we cut out some neurons, there might be an issue that people can easily defeat with an adversarial picture or something like that. So yes, more testing is needed when we do this kind of deployment. So network pruning. Network pruning is removing redundant neurons. There are two types. There is static pruning. For example, when after we train the neural network, it will look like this. It's the exact architecture when we design it to be, right? But sometimes there are weights that are really small, or there are weights just there's no use at all. So we do testing, like can remove this and test if the neural network is performing the same thing, right? If it's almost the same, then we can just bet off like cutting this or cutting some connections, so that like we don't have to do this useless redundant computation. There's also dynamic pruning. Dynamic pruning is we're probably going to have a live decision component. Like, for example, if this neural network is doing object detection in a rainy day, maybe some neurons are not useful. And this live decision components can detect that. I mean, they can just shut off those neurons so to improve the computation speed. And another time maybe it's a sunny day, then maybe those neurons are useful and they can turn off other like redundant neurons. So there are these techniques to help speed up the neural network performance in the deployment procedure. Quantization is, first we can reduce the size of the neural network. That may be an issue for mobile or embedded platforms. So the technique is that For example, if there are small values, or if there are values are quite close, can we just put it into 0? Like we quantize the floats inside the neural network into some centroids. This will reduce this computation and the size of the neural network. Here's another example of how NVIDIA quantize the neural network from a float to integer. So when we change something from float to integer, it's not just the speed, it's not just the precision changed, it's also the dynamic range. They have to find which are the useful dynamic range inside this neural network. Then try to find the correct centroid over here and use the 8-bit integer to represent to the best possible extent the original neural network. So there are different platforms we can deploy, right? There is CPUs, GPUs, FPGAs, or mobile SoCs. Depending on what type of platform you use, you need to use the platform-specific packages for deployment. Here's another diagram of different kinds of devices in the market for deep learning deployment. We can see our Xavier is here right in the middle. It's denoted as a float 16 device. That means our Xavier has some tensor cores that will function well in the float 16 precision. There are some platform optimizations that you can use. We can have a lookup table just to save repeated computations. Or we can do memory optimizations. Some chips might have very limited memory bandwidth. So there could be special optimization that you can do. Maybe you shouldn't use the memory access at the same time. You can spread out that memory access, or some other techniques that you can use. There are some special hardware optimization libraries. For example, this QDNN is CUDA deep neural network. It's developed by NVIDIA. So these libraries, they may have some special instructions on the chip that those engineers can use, so that if we just apply our neural network with this type of library, we automatically can get a performance boost. So when we do the deployment on different platforms, there is a common format that I want to introduce you to. It's called ONNX. So ONNX is a open source tool to parse AI models written for a variety of diverse frameworks. For us, with the Jetson NX on the F1TENTH car, NVIDIA TensorRT is the SDK for us to do the deployment. So it includes a deep learning inference optimizer and a runtime. So when you run the neural network through the optimizer, it will automatically optimize it for you. It's a black box, but it works great. When we want to run the neural network, you need to use the runtime to run it. It is very easy to use, but it's only for NVIDIA platforms. How do we generate this TensorRT engine? So we first need to convert from whatever training libraries we use into this ONNX format. Then we run it through the TensorRT optimizer to get a serialized engine. And when we want to run the engine, we need to use the TensorRT runtime. The serialized engine is platform specific. That means you cannot use the generated engine on a different hardware, even a different version. For example, if you have a different version, JPEG version for the NVIDIA Jetson NX, you may or may not be able to use the engine generated by an older version. It supports FP16 and integer 8 quantization. It also supports dynamic shape. So you can actually change the input dimension when you do the runtime. For example, if you want to have a larger input size. With a larger input size, you can detect better with smaller objects, right? So they actually support this type of runtime change of the input dimension. That's the end of this lecture. Thank you for your time and good luck with your lab assignment.